So now that you know a bit about the Reactive Streams API and the Reactive Programming Model and a little bit about popular implementations of the Reactive Streams API, let's map Reactive Streams onto the Reactive Programming Principles. We did something like this earlier when we talked about completable futures, but now we're going to focus on the features that are available in the Reactive Streams API and popular implementations therein. And you'll see again that the four main principles we're concerned with here are responsive, resilient, elastic, and message-driven. So we'll start with responsive. So the goal for responsiveness in this context is to avoid blocking caller code. We don't want to have to block the caller because when you start blocking, that underutilizes processor cores, impedes the inherent parallelism on multiple core processors, on modern multi-core processors, on modern processors that support direct memory access, modern processors that allow overlapping computation and communication, et cetera, et cetera. And it will also complicate the program structure by putting blocking in because you end up having to create all these threads that run around on the client side, and it gets tricky very quickly. The way this is handled in Reactive Streams is by using various operators like subscribe on, publish on, and observe on. And these are operators that are supported by either Project Reactor and/or RxJava. And they're used to inform the runtime system where the computation should be performed. And we'll talk a lot about that. You'll get a chance to play around with those things. It's very powerful and interesting, although a little bit convoluted in some ways compared to parallel streams or completable futures. And we'll talk about that as well. Another way to make your programs more responsive is to avoid changing threads. So sometimes we want to avoid blocking caller code, but other times we want to avoid changing threads, because if you change threads too much, you can actually end up incurring excessive overhead with respect to synchronization, context switching, memory management, cache management, and so on and so forth. And therefore, we'd like to find a way to give programmers tremendous control over when you change between threads and when you don't. And again, the way this works is we use these operators like subscribe on, publish on, and observe on to get very fine-grained control over where these events are mapped and processed in given threads. And you get a lot of flexibility here again. And you can, we'll see in a second, you can control other things too that give you a lot of flexibility and power. Another important reactive programming principle is resilience. And what that basically means is you don't want a failure in one part of the system to cause the whole thing come crashing down. And the way we do that is by using exception methods and exception handling operators, which decouple normal operation processing from the processing of errors when they occur. This, again, will look very familiar for those of you who remember the discussions we had about exception handling methods in Java completable futures. Similar kind of idea here with reactive streams. Always remember excuse me, that reactive streams, like completable futures, like parallel streams, are localized to a single process on a single computer, not a cluster. If you want cluster programming, you'd have to use something else like the Spring framework or Hadoop or something. Yet another reactive programming principle that's very important is the concept of elasticity. And the basic idea here is we want to be able to have these asynchronous computations that are part of these operators we just talked about, run scalably in a pool of threads atop a set of cores in multi-core processors. And there's a whole slew of different schedulers that RxJava supports that allow you to indicate where you want your computations to run. Do you want them to run in a pool that's associated with I/O-bound work? Do you want them to run in a pool that's associated with computation or CPU-bound work? And then there's all kinds of other crazy things too. There's about a half dozen or so different kinds of schedulers, and you get a chance to play around with some different ones. The other cool thing about this is you can plug and play schedulers orthogonally or independently with different types of streams pipelines. So you can decide as a very late binding mechanism what kind of mapping you want between your events in your stream and the thread pools that will process those events as it flows through as they flow through the stream. Project Reactor also supports a bunch of different threads and thread pools, although our primary focus here is on RxJava. Much the same kind of idea. And then the last piece of the puzzle here is the ability to support a message-driven architecture. And this shows up in a whole bunch of different ways. There's various thread pools that are implemented by message passing, such as the common fork join pool. Project Reactor and RxJava can work with the common fork join pool, but they also have their own thread pools because they want to do them in a slightly different way. And those have message passing, of course. And then the implementations of reactive streams themselves do a lot of message passing internally behind the method-oriented API that they expose to you. So that's the end of a quick overview that maps the reactive streams concepts onto the reactive programming principles. It's probably worth noting here that although Completable Futures does a pretty good job of mapping onto these principles, especially when you combine them with Java sequential streams, the reactive stream stuff, surprise, surprise, is even better tuned to work with reactive programming principles, because after all, they're reactive streams.